Welcome back, students, to the second part of our discussions from the lesson Atoms and Molecules. In the previous class, I had told you that how the concept of atoms was thought of around 500 BC in India by an Indian philosopher, Maharshi Kanad, who postulated that if we go on dividing matter, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. This ideology was supported by another Indian philosopher, Bakur Katyayana. Around the same era, ancient Greek philosophers Democritus and Leucippus also suggested a similar theory. Democritus called these indivisible particles atoms, which means indivisible. All these philosophical considerations got an experimental validation in the late 18th century. Two important laws of chemical combination were given by Antoine L. Lavoisier and Joseph L. Proust, namely law of conservation of mass and law of constant proportions, about which we had discussed in full length detail in the previous session. Now, once these laws were proposed, the next problem faced by scientists was to give appropriate explanation. That's when British chemist John Dalton came up. He provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was still then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. This theory actually provided an explanation for the law of conservation of mass and the law of definite proportions. Now, before I discuss more about Dalton's atomic theory, let me tell you a bit about the life of John Dalton. John Dalton was born in a poor weaver's family in 1766. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. So, what was Dalton's atomic theory? According to Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of his theory are right now coming on your screen. All matter is made up of very tiny particles called atoms, which participate in chemical reactions. Atoms of a given element are identical in mass and chemical properties. Atoms of different elements have different masses and chemical properties. Atoms of one element can combine with atoms of other elements to form compounds. The relative number and kinds of atoms are constant in a given compound. Atoms are indivisible particles which cannot be created nor destroyed in a chemical reaction. So these were the important postulates given by John Dalton, and according to this theory he proposed a model for the structure of atom which is something similar to that of a solid sphere ball or a bowling ball. That's why it is called bowling ball model. And with the help of this structure he tried to explain the law of chemical combination, as you can see in the picture right now on your screen. Even though his theory was a major turning point in the study of matter, yet there were a couple of drawbacks. Dalton said that atoms are indivisible, but we know that atoms can be further divided into still smaller particles called electrons, protons, and neutrons. He again said that atoms of an element have exactly the same mass, but they can have slight difference. He also said that atoms of different elements have different mass, but some atoms of different elements have the same mass. All these things will become pretty much clear when we discuss in detail about these topics in the next half of the chapter. We shall be discussing more about the structure of atom, the properties of the subatomic particles, all these will be discussed in the later half of the lesson. So, but majorly what the drawbacks in his theory would become more clear to you all. But right now, one particular question might arise in our mind, that the theory, as it suggests the existence of a smallest indivisible particle, actually what is it? What is an atom? Now for this, let us consider an example. All of us might have observed a mason building walls. From these walls, a room is made, and then a collection of rooms forms a building. So now, if a question is asked, what is the building block of that huge building? Obviously, the construction begins with one brick. From a brick, a wall is made. From walls, a room is created, and obviously, a collection of rooms contributes to form a huge building. Say, for example, you consider an ant hill. What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. Let me show you in a bit more detail how does an atom look like. As you can see, in the center, one dot is shown, and inside that small dot, it has been enlarged and it is written 1 FM. 1 FM stands for 1 Fermi or femtometer, which is equal to 10 to the power minus 15 meter. So you can see some subatomic particles have been shown, but we shall not discuss about these right now. We shall only discuss how does an atom look like. This is exactly how it looks like. I will also show you the picture of an hydrogen atom. See, this photograph shows the atom's electron orbital, the first time we have ever been able to observe the wave function of an atom. It is actually beyond the syllabus, actually beyond the scope of your syllabus, so you shall be studying about this more and more in your senior sections. But right now, just for the sake of understanding how does an atom look like, this would be perhaps the best example. So this is actually how an hydrogen atom looks like. This is one more such example. So atoms are actually very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms when stacked would make a layer barely as thick as the sheet of the paper of your notebook. That's why atomic radius is sometimes measured in nanometers or angstrom. 1 nanometer is actually 10 to the power minus 9 meter, and 1 angstrom is 10 to the power minus 10 meter. Now, at this point, I would like to introduce the concept of symbols. As we all know that when it comes to representing any quantity, it is quite convenient to represent a quantity using symbols. Now, this concept of symbols has been thought of for the time of John Dalton. Actually, Dalton was the first scientist to use the symbols for elements in a very specific sense. What was that? When he used a symbol for an element, he also meant a definite quantity of that element. That is, one atom of that element. Right now, the first list that you can see on your screen is actually the symbol suggested by Dalton. You can see the name of the element and Dalton's symbol. So whenever you are making, suppose the symbol for hydrogen, if suppose I make this symbol, then it represents one atom of hydrogen. So a similar pattern you can see has been used for several other cases. Now at this point I would also like to show you the combination of these symbols. See how he made one molecule of water. See, one molecule of water, one molecule of ammonia, using the symbols that he had suggested. This is one molecule of nitrous gas, one molecule of olefin gas, carbonic oxide. When it came to using 3 atoms, one molecule of nitrous oxide, one molecule of nitric acid, this was actually the symbolic representation of several compounds. can also see how he had shown one molecule of nitrous acid, one molecule of acetic acid. So in this manner, symbolically, different elements and compounds were shown. It was actually Berzelius who suggested that the symbol of elements be made from one or two letters of the name of that element. Again, there was a confusion. In the beginning, the names of elements were derived from the name of the place from they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC, that is International Union of Pure and Applied Chemistry, is an international scientific organization which approves names of elements, symbols, and units. Many of the symbols are the first one or two letters of the element's name in English. The first letter of a symbol is always written as a capital letter, that is, it should be in uppercase, and the second letter as a small letter, that is, it should be in lowercase. For example, for hydrogen it is H, for aluminium it is A and L. So going by the rule, the first alphabet is written in capital and the second alphabet is written in lowercase. For cobalt it is CO. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Like for example, for chlorine it is Cl. Similarly, for zinc it is Zn. Other symbols have been taken from the names of elements in Latin, German, or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium. Potassium is K from calcium. Therefore, each element has a name and a unique chemical symbol. As you can see right now on your screen, a chart has been shown in which 60 symbols have been shown. The name of the elements along with the corresponding symbol, that is clearly shown. So you need to remember the symbols of some of the important elements so that it becomes convenient for you to write down the chemical formula. Now this will be the topics of discussion for today. We shall continue with the next topics in the chapter of atoms and molecules in the coming sessions. Thank you.